All right. Well, it's great to be here. Good morning, everybody. My name is Mohamed, and today we'll be chatting about some of our thoughts on best practices to build a robust, systematic model testing process and automatable as well for our organizations. I can actually walk around. Quick personal introduction. Thanks, Shilpa, for a great intro. But really quickly, I am CEO and co-founder of Kolena. We are building a test harness for machine learning teams to help build their robust testing processes and automate these workflows. I wrote Manning's book on computer vision, deep learning for vision systems, and previously led AI organizations at Amazon and Twilio and Synapse, which was acquired by Palantir. Now, since I'm introducing myself, gotta be honest here, I have been burned by a lot of model failure incidents throughout my career. Not very proud of it, but my only consolation is I'm sure a lot of you folks here have seen some of these and have experienced your fair share of these failures. Quick show of hands, does anybody relate to this statement here? Pushing model, oh, that was faster than I thought. I would love to hear from you, people who have seen that, and get your thoughts on what we're working on. And people who did not raise their hands, I would love to know how you actually got to this model confidence in this process. But real quickly, is this working? Oh, yeah. Real quickly, just quick agenda of what we're working on here. So we worked throughout the years in my personal career, building models, work with teams, and put the model in the system, and then push that system into production. We see tons of surprises on what edge cases that we thought we fixed and regressions. Model regressions happen every single time. That's guaranteed. And we need to put the process of debugging the model, looking at images, videos, LiDAR scans, depends on the problem you're working on, takes weeks. And because of that, it's really hard to set up a robust process for it. We put our blueprint here. We'll be talking more on the technical level, not on our product level. But these are best practices that this is a computer vision summit. We're talking focused on computer vision problems, but these apply for other language problems, large models problems, multimodal and structured data. So first, we want to start thinking about our model testing at the scenario level, not the class level that we are using now. So if we're building a model, and you'll see an example right after the slide, if you're building models, we track them usually at the class level, building a car detector. My car detector is 99% accurate in detecting cars, but how is the model performing at these different weather conditions, noise conditions, depth conditions? There are tons of scenarios that are abstracted by this global metric. And then this doesn't provide us the right visibility on how our test data is representing that production environment. Second, we want to start talking about regression testing. How can we build this growing list of institutional knowledge base of all the scenarios that we've been seeing throughout the months and years working on this problem, and make sure that we're always adding to that and no scenario or no subclass is left behind when we're testing our models. And this is a way to allow us to chase that long tail of edge cases as we work through the problem. Last but not least, we're done scenario level testing, we're done regression testing, we're good with this model, but we should not push to production in most cases without product level testing. Product level testing here, we're talking about a model that sits in your system. Your system could involve pre-processing scripts, post-processing processes, or a pipeline of a model feeding the other. We have an example of that, and the results change. Another thing is product level metrics. We are looking at traditional ML metrics like precision recall. All these can very much be misleading into making the right decision, which is the best model to that customer. And last thing is the integration testing. Our models, we're testing them in our environment. We push it out in production on different hardware, and we want to make sure that, and sometimes we package it differently, we want to make sure that we're testing closest as we can to the production environment. So next I'm going to jump onto each one of these. Scenario level testing. All right. So this is a story that I like to share. We're talking about how we've seen these experiences in our careers. At some point in my career, I was working at a startup called Synapse. We were building weapon detectors in X-ray machines, went into a customer demo, and presented a model that's scoring 99% on recall in detecting the gun class. Now, obviously, you probably know what's coming next. We had a lot of confidence in this model. A customer in the demo pulled a gun, dropped it in empty bin. It was an airport security checkpoint, and then passed this bin through the X-ray machine, just gun empty bin. Very simple case, and we missed this case. Now, chances are, when we, as ML engineers, say my model is 99%, we assume that the 1% here is the most adversarial case. A more embarrassing fact is we actually seen this failure mode internally a few months before that demo. It was good. But models, when we train them and retrain them on different data, these parameters are usually almost always pulled towards a different direction, and you see regressions in scenarios while the top-level metric is still showing improvement. This takes us to a phenomenon that researchers have labeled as the hidden certification problem. They basically say here that this model exhibits high valuable performance across these scenarios within that class. And we should not be looking at this top-level metric because it doesn't tell us exactly any actionable insight where the model has improved or regressed or which model is better. And we almost always see models fail silently. In this example here, I cited the paper for you guys. In this example, the researchers, the authors of the paper, went through a case study in a cancer detector in X-ray imagery, chest X-ray imagery. And they saw, I don't know where the pointer is, but you can see here, they saw that this aggregate curve, the blue curve is the aggregate metric, has been skewed by less important slice of the data that has chest drains. Doctors add chest drains into the image to mark them as cancer patients. But the actual important slice of the data or scenario is performing way less, which is the green curve, way less than the aggregate curve. So we always see that when we are working on these global metrics for the class, we're misled to believe one model is better than the other or one iteration of the experiment is better than the other. And we always go put a lot of effort, spend 60 to 80% of our time as engineers debugging this model, trying to verify these assumptions. And the way we debug them, we look at these data points, whether it's images or videos, or it gets harder when videos are LiDAR. You go through these data points one by one and try to find patterns in our head and look at our notes. In the last experiment, we saved this and we improved on that. And we are presented always with this V1 of the model, and that's what I was presented with with the gun example. V1 of the model is 96% on F1 score, and that improved into 99%. Now, this level of information doesn't tell us exactly which model to deploy. Is the 99 better than the 96? We have no idea. That's what we did here with the 99. Are there any regressions when we improved the top-level metric from 96 to 99? It's not clear for that. We have to dive really deep into data. What's the test coverage? Question that I believe every ML engineer or manager has been asked. What have you tested on? Did you test on the new data that we got from that customer? Did you test on this? We just added the golden data set. We have been improving and adding these scenarios. So have we thoroughly tested our models is a question that we always get from non-engineers, like in product areas, even your customers. And we're not able to showcase what's our testing process other than saying, hey, we have a rigorous test data. That takes us to the scenario level testing. This builds a process of a systematic and robust way to test our models that is reliable and can be automated. So in the same example, V1 versus V2, we're looking at some scenarios that we would be tracking. So V1 of the model, while performing lower in the top-level metric for the gun class, it was performing very well in the gun empty bin case and other basic orientations of the gun, simpler problems. Now, when we tried to improve robustness for high occlusion and high blur, we went into the second iteration. We did improve on that, and that was reflected in the top-level metric, 99%. We pushed it to production. We were so happy. But we did not notice that the model has silently regressed in a critical piece, like the gun empty bin. And that allows, we'll talk about this more later, but allows this level of high resolution or level of visibility allows automatability of this process. If you want to make sure that you're always giving your customer a better product, then you can assign these kind of pass or fail criteria, critical scenarios, or critical areas that you want to deploy only if there are no regressions. You see these red arrows up there, and green arrows up, red arrows down. You want to make sure that, because the list doesn't, you will see that in the next slides, the list is not only 6 or 7 test cases like this one. It will be in tens when you have a robust process. You will have these in tens and hundreds. So this way you're allowed to automate this process, push 50 models up there, and then push the right model to production. So with that, we want to make sure that we look at how we manage our test data in a different way. Everything we know about our model or our product before pushing it to production is coming from this test data. ML engineers use the test data to guide their development and understand the model performance. Product managers, they need to use the test data to encode their product requirements. They are closer to the customer, and then you want to make sure that these customer requirements or the deployment requirements are represented in the test data. Other business folks, like be it biz dev, sales, your customers, they look at your results of your test data to understand the product that you're building. So we're making the claim here that properly managing your test data is way more important than your training data. Training data is not meant for us to represent all the scenarios out there in production, right? Because the whole point of training a machine learning model is you're training it to generalize to unknown scenarios. Now, the ideal scenario or the ideal case, on the other hand, is you're able to build the right list of test data that represents all the scenarios out there. That's what you need to be growing more and more. And when a scenario is not performing well in the test, this is when you start considering adding it in the training. So this paradigm shift from the world that we live in today that has unbalanced and arbitrary split benchmarks or test data set, we want to move on to a world where we have, it's coming now, I'll try to. All right. A world where we have a more fine-grained and well-curated test cases. Now, this was the gun example. Instead of having some bulk of data of whatever you're working on, you want to stratify it into scenarios that are more representative to your product. Now, these examples here, you're looking at object-level examples only, like orientation and so on, but there's tons of slicing strategies that are different that we need to consider. Example of that, the gun and empty bin scenario that we filled in, it's not because the features of the gun are not clear, it's just because the model was trained on a much smaller bounding boxes, and when the bounding box of the gun grew bigger, because this was the only object in the bin, the aspect ratio grew, and that threw off the model. So characteristics like, other than characteristics that we look into, like the object itself and brightness and all basic stuff, and blur and others, there are characteristics that neural networks get confused by and get biased by, like the mathematical ones, like the aspect ratio of the bounding box, number of bounding boxes or number of objects on the screen can throw off the model, and others as well. Having this is the last slide on this scenario testing. Having this list allows us to find the blind spots in our tests and make sure that we are actually having high fidelity tests. In this graph, you're looking at the red curve. This is the model performance for a specific class at different scenarios or different subclasses of that class. Now, the blue curve here is the distribution of your test data for these different scenarios. And you notice here that while the model is performing very poorly on subclass D, it will still give you, if you're looking at the top level metric, it will still give you a high score without having this kind of visibility. So that was scenario testing, just thinking about your data in a different way and find a way to manage that. Now, scenario regression testing is what we're going for here. Now, you saw a list of few test cases. You always, when you start a problem, you're not expected to just sit with on your computer or a notebook and just list all 100 possible scenarios that are coming. That's not how it works, because you need to work through the problem and you need to understand, have a deeper understanding of your domain as you go through your project. And that's how we built a quality flywheel and you need to have in your infrastructure in like a dynamic test harness that helps you go through this flywheel really quickly to get deeper understanding and grow this list of knowledge base. So let's say an example of we have building a car detector again. Initial understanding, let's say you're starting project today, you start saying, okay, I want to find my model, or I want to validate my model results in different, weather conditions and lighting conditions, so day, night, and rain and snow, just something simple. Usually, we've seen teams start with 10, 15 test cases because they've been working in the problem, and then this grows exponentially very fast. So first, you start listing the basic understanding of your domain, and then you go ahead with the vetting or testing your model at this level of granularity. Instead of a car as one object, it's more like you're looking at 4 scenarios now. And in here, you see the green curve in the bottom. This is showing that the rain, you probably won't be able to read it here, but this is the rain curve, and this is how your model is performing when there's rain weather type. So with that, you start diving deep into that rain scenario, go into the data, and look into just this slice, and have deeper understanding of these failure modes, analyze them, and create more granular test cases. And this is when you started with just some weather conditions into different weather conditions, different occlusion levels, different noise conditions. And this is just an example. Across of those would make around 60 test cases. So you start the cycle with few test cases, and then you grow really quickly into tens and hundreds. And this should be obviously version controlled and managed. Having done that, now you started building that institutional knowledge base of edge cases. Every engineer in your team is finding an edge case. They add it to your test case manager. Every engineer debugging somewhere else, you're adding that. So this always growing, and you make sure that there's no scenario that is not being tested every time you update the model. Everything is tracked. And this becomes your quality criteria for your product, this list. Instead of looking at a list of car data, that's all I'm doing. Now we're looking at Mohamed joined your team today and learning from the years that you've been working on the problem. Do you see that, okay, you have, for the car problem, you're testing against different car orientation, different types of the vehicle, and different light and weather conditions. You start having these test coverage conversations with your customers, with your product, and build this team alignment and trust. Now, when you have this list, you're doing model comparison again. You're looking at, these are 2 models, YOLO R and YOLO X. Just a simple example, same car problem, but you're looking at the top level metric for the YOLO R is 96%, and for the YOLO X is 98%. And you see that the YOLO R, which is the 96, is our champion, and we just trained a new model, and we want to see if that should be our new champion. And on the left here, you're looking at different test cases. And this is a growing list, obviously. So you see that we have the model that we just trained has a minor regression in the black and white images. And this is from 81% F1 score to 79%. You can decide to ignore that or act upon it. And you have another larger regression which is in the interior view, being able to identify the vehicle when the camera is inside from the driver's dashboard, and went from 72% to 58%. So while that new model, YOLO X, is better in all scenarios, it has 2 regressions here for you to decide whether you don't care about these scenarios or you want to act upon them. This is the last thing on the regression suite. Make sure that your team is really deploying the better model, giving the better model to your customers, and the team is not playing whack-a-mole, which is always the nature of our machine learning work. We're looking at a bug, we squash it, and then it show up again, and then we keep squashing the same thing, and we're going through this loop. Right. Last and the most interesting part of it is the product level testing. We test our models, but we need to test our systems too, like the end product that's going to our customers. This is a critical part of a comprehensive testing that we are often always dismiss it, whether for time or for lack of infrastructure. But we have a case study here that we ran on the GAD data set. It's an open source data set here, and the project is to identify a pedestrian crossing and classify them whether they are crossing the street or not. In this case study, we had a system that includes two models, a pedestrian detector, it's like an object detection problem, and then it feeds into a classifier to classify whether this pedestrian is crossing the street or not. And the goal, obviously, of this product is to avoid collision with pedestrians if you're in autonomous vehicle space. In this case study, we ran a few open source models, like sort and deep sort for the detector, and C3D and static for the classifier. When we tested each model on its own, we found that the deep sort is a better detector, and the C3D is a better classifier. But when we test the system, in general, you probably know where I'm going with this, we found that the winning pipeline really is the sort and C3D. And the reason here is deep sort was too good that it detected pedestrians that don't matter. The classifier failed on those, which again, doesn't matter. Now that you are testing the entire product, you want to make sure that you actually have metrics that is reflective to your problem, not the traditional ML metrics that we use, precision, recall, and so on. So on the same problem, same case study, we looked at a tested system A, system B on false negatives. Recall is important for this problem because you want to make sure that you're not detecting or you're not missing a pedestrian and leads to a collision risk. But looking at recall only or false negatives only for that system, you will see that system B is better because it missed only 30 pedestrians versus system A that missed 100 pedestrians. So that's what recall will tell us, deploy system B. But adding a simple logic for another product level metric like collision risk, you say that, okay, collision happens, or there's collision risk happen if there's a false negative and if that pedestrian is closer to within the 10-meter range. Because if you miss a pedestrian that's far, it doesn't matter. You will get them when you get closer to them. So with that, you will notice that system A, while it missed 100 pedestrians, but most of them were far enough that there's no collision risk. It made actually much better system for that metric to deploy versus system B. Last thing, integration test. We talked about it a little bit, but real quickly, models lose sensitivity, lose performance when you put them on deploy on different hardware. They have different deployment conditions. We want to make sure that as we're comparing, you test the best experiment, you want to put it in the best system, and then you want to test that on the deployment infrastructure. Now, closing note, totally understand, worked with the last few years with hundreds of teams, and this is one of the hardest problems, chasing that long tail and making sure that we're always improving, and we have this knowledge base that goes through regression testing. So we understand that this is a hard process to build, and the culture of quality in our organization doesn't come from one heroic act from an engineer in the team or a breakthrough in neural network architecture. These things have been commoditized and are available for us. But what we need to look into, the way we see it, is we need to set up the infrastructure or the process into seeing high resolution testing at the scenario level, like high granularity, build a standardized way to grow our regression test. This is the institutional knowledge base, and build a systematic process at scale. So we have 2 engineers, go to 10, to 50, and it's always working the same way. We built Kolena to make this process robust and simple. I'm right here at the booth outside if you guys have any questions, if we don't have the time if you're here. And yeah, please connect with me. People who had the problem, who don't have the problem, would love to hear from you. Thank you.
Where is this compatibility test is done?
Where is the what?
Compatibility test, which includes the hardware and software both, OS level.
Where is it done?
Yeah.
So that's the, yeah, so the question is where is this integration test should be done? In here, we recommend integration test, and we recommend you build infrastructure for that. For our customers at Kolena, we take the way you actually are testing your models, you're testing your model on your environment, whether it's a training environment or test environment or the integration environment. And using our Python client, you push the results up onto Kolena. So this is how we did it. If you have an internal system, you want to make like internal infrastructure for the testing, then you want to allow it to get the results delivery to test the end-to-end system. Or solutions like Kolena, we allow you to test end-to-end on your environment so as a black box, input, output, and push the results up onto Kolena with your metrics.
Hi.
I've seen that when you build the application, you have a set of hardware, and then you have a set of GPU, OS level, and then later on, when you are in the final stage, you say, oh, we got new hardware level, and
yeah.
new hardware is not being developed.
So yeah, I mean, you need to test that. So if you have new hardware, then you probably want to test on that. That's what we're recommending, yeah. Correct.
What's your method to classify the test cases to make sure that there's no edge case is left?
Yes, so this is a very good question because we built a component just for that. We call it the Test Case Studio. And this is, again, no magic would allow anybody to jump through the years of learning the problem, but we can make it much shorter. So we built a component studio here. We allow you to manage your data and visualize the data, and we point you towards the right slicing strategy. Like I mentioned here, if your data if a scenario is not represented in your test data, I don't believe there's a system can tell you, hey, go ahead and collect that. But for us, we do that. We build a recommender system from the learnings on our test. All the tests have been ran on Kolena. And we tell you, hey, you're working on a face problem, for example, face detection problem. We see that you don't have high brightness represented in your data set because we understand that high brightness affects the model performance heavily more than darkness. So with that, this is what we call the network effect. We have our data science team working on model results and understanding for each domain what are the right slicing strategies, what are the right edge cases. We present them to you as an expert in your domain as a recommender. And you decide to slice your data with that, or if there's no data present with this scenario, you need to probably collect that first for the test data.
Hello. I was curious about in the scenario testing, when you showed for the gun cases, you were talking about there's low blur or like high blur and the back view of the gun. Now, how do you do testing for like the combined scenarios? There's both low blur and the back view. Or due to double dipping in those type of test cases, or are there combined metrics that we need to see?
So you're referring to two bounding boxes in the same frame. One is side view, one is rear view. Is this what like two represented in the same image?
Yeah, it could be both in the same image, or like a single object that has both aspects to it.
Yeah, so because I'm trying to wrap my head around the same object. Let's say me, Mohamed. If I'm on the screen, I'm either facing forward or facing on the side. So are you talking about the same object, two objects in the screen, looking at different angles?
I'm talking about if I have an image of you that's blurry while you're facing forward.
This is a good, thanks for explaining that. Yes, that's what I meant by the flywheel here. So example here, you broke your data down only to gun side view, right? You don't have blur in your data yet. And then when you probe further on the failures for that slice, you have much less data to look into. And then you notice exactly the same debugging that you do, you notice that most of my failures in this case is because of blur. So you're going to break this scenario into two. It should be you have a system, like for us, we make this process happen in minutes, that you're looking at a scenario that I'm missing a car, a train, And then you notice most of these cars that rain are cars that rain at night, more car and rain and fog, car that rain and side view. So these are the main 3 reasons the car and rain is failing the scenario. And you break that 1 test case into 3 test cases. And this way you're able to probe further really real quickly into why you're failing. Is it because just rain, or is it because a scenario in that is failing, a specific scenario that you need to improve?
Just to clarify, are you saying that these scenarios need to be independent of each other?
I mean, the higher resolution, the better. So again, the same example, if you're doing a face detection problem, you can say, here's my results for male versus female, right? But and then you can probe further in saying male and race. So you have now 10 test cases, more than, it's not just 2 genders, it's 2 genders and 5 races, so that's 10. And then you break it further into age. So you keep cross-multiplying these test cases they can be not independent, but if you make them higher resolution, more granular, more independent, you will makes your debugging much faster, and you'll get you to narrow down to the problem much faster. So we do recommend that you probe further. If this is a scenario that you care about, that you're improving, probe further and understand 4 or 5 levels of depth into why this is failing. So for me, it would be like a male, adult, race, a beard, and profile view. So something like this, like 4 or 5 of those characteristics gets you very deep enough, and you will find yourself really quickly have hundreds book in one class, like a car or a face, into a couple hundred test cases. And that allows the full automation, if you get to that level, full automation from training to testing to deployment, by assigning no regressions in important cases. Cool. Thank you, everyone.